Well, a bit. This video is made for me to explain a new approach, I guess, or rather another approach to do the classification given your acceleration data, right? So this is an approach using fuzzy logic. So the inputs, we have three inputs to this fuzzy logic model, you can call it, and we have three outputs of the fuzzy logic model, and each output will give you a prediction whether it belongs to a certain speed or not. So for example, output 1 will indicate whether the data is speed 0, output 2 speed 1, output 3 is speed 3. So so I'll be giving you this file, and I'll advise you to run this file by section, as you can probably see here. Right, so this first section is just about just on importing data, get the number of rows, and here we do, sorry I haven't commented, but since I'm doing this video I guess I don't have to comment it. So this part here, we are separating our data into training data set and test data set. So this is training data set and this is test data set. Apologize for the lazy variable name selection, but here you have underscore test, so you know this is test data set. And here is where we change or convert, or should I say we compute a quantity that I call the mean absolute deviation around the mean. But in our case, our mean here is our moving average. So you should study about moving average, and you should absolutely read about this mean absolute deviation around the mean. So for our fuzzy logic model, we have three inputs, like I said. The first input is the mean absolute deviation around the mean of x, the capital X. You know, each of your file you have x, y, z acceleration. So the first input is the mean absolute deviation around the mean of x. The second input is of y, and the third input is of z. So the fuzzy logic model will be giving a score of three different speeds based on these three inputs. All right. So on the second section of the code, you can just click run section. You will see this is the plot of the three files that you gave me. So this is for, sorry I haven't labeled the axis. This is, I guess, for speed 0, this is speed 1, this is speed 2. The red plot is x, green is y, and blue is z. And the black plot is the mean absolute deviation around the mean. So if you read about this, the mean absolute deviation around the mean will give you a measure of, I guess, a measure of dispersion or spread of the data. So somehow I could see that if we can make use of this spread of the data, we can do a better prediction. I don't know how I discovered that somehow, but anyway, we can discuss that some other time. So these are the plots. So the input to our fuzzy logic model is the black plot. Okay, so I'll just close this. And this is histograms. Okay, so as you know, histograms can give you a sense of distribution of the data. All right. So this is for data 0, data 1, and data 2, and respectively the x, y, and z values. So the blue is the histogram, but the magenta lines, I have to construct these triangular lines by trial and error to be used as our membership function for our fuzzy logic model. So if you remember from your undergraduate course, or if you don't, I can give you a link on my online lecture. So if you remember, for our fuzzy logic controller, we have to have membership functions. So we construct our membership functions from the histogram of our mean absolute deviation around the mean. So this is not really the data that you gave me. This is the mean absolute deviation around the mean, right? So once again, we use the histograms to construct our membership functions of our inputs. So I had to play around with these values. All right. So for our triangular membership functions, you have A, B, C. So A is the first edge, you can call it. This is B, this is C. All right. So I have to manually tweak the ABC values so that roughly my triangle fits nicely over the histogram. Okay, so you can see like we have 9 sets of ABC. So 1, 2, 3. This is only for X, and we have for Y, and this is for Z. So once we have that, we can construct, actually we have constructed our membership functions here. We can plot it so that the maximum value is 1. So this is how it looks like, right? Sorry, this is output. So we do this to get this membership function. So this becomes this, and this plots becomes this plots becomes this. If you can compare, these two sets of triangles are the same except for the amplitude. Right here the amplitudes are always maximum 1. Okay, but the horizontal points of ABC are the same. Okay, and the membership functions for output is this. These are output membership function. So as maybe you remember in the last stage in fuzzification, in fuzzy model, is defuzzification. So defuzzification is a process we convert aggregated fuzzy set to crisp value. So we need to generate a value from this horizontal axis. Remember, like I said earlier, we have 3 outputs for our fuzzy model, and if this is sorry, I think I made a mistake. The output is only 1, right? The output of a fuzzy controller is 1, but if the output is between minus 0.5 and 0.5, that means the prediction is 0. Okay, if the output is between 0.5 and 1.5, that means the predicted speed is 1, and if falls in between 1.5 and 2.5, the predicted output is 2. So let me correct myself. For our fuzzy model, we have 3 inputs and 1 output. Okay, the output is numerical, and we will determine the predicted speed based on in which range the value falls. Okay, and this is the membership functions for our output. Close this. So now we have constructed the membership function. So from all of that, all that we have done so far is just to construct the membership functions. Okay, so this is the actual computation or prediction. Okay, I'm not going to run this because it takes some time because you have a lot of data. So before I go through the code here, let's see the results. So this section of codes will do model evaluation and model validation. So you should know the difference by now. And as we can see, when we give in data 0, right, the evaluation accuracy and validation accuracy is given here. It's 0.99 of both, which is very, very good, right? So you might be wondering, what are these two, right? So because the way I wrote the code, I compute the accuracy for all classes, right? So this is accuracy for class 1, this is accuracy for class 2, and this is, sorry, class speed 0, speed 1, and speed 2. So 0 means we don't have the output between the range of the range that you saw earlier, right? What was it? 1.5 to 2.5. Okay, so class 1 and class 2 is not predicted here. You only have class 0. And so so if you want to give in data class 0, you have to comment this out. Okay, so you have to comment these two out. So this means you are evaluating and validating the model for data 0. So you will get all this. Okay, next, if I want to check the performance on data 1, I have to comment this out and uncomment this. So I will get this now. So this is for data 1, which means you expect the output, the predicted output to be speed 1. So indeed, when we check the accuracy, evaluation accuracy 1, so 98, this is 99%, and this is also 99%. Very good, right? So next, for data 2, 012, data 2, so we have to comment this out and uncomment this and run this section only. Okay, you don't have to run the previous sections. Only when you want to run the model, you just run this one. So the rest you run only once. Okay, so when you run this, I get this, the last chunk of display. The accuracy is 98% and 96%, slightly lower, but it still is good. Of course, the data that we have is simple data, that's why the performance is very good. But I believe you can write a paper using the data that you have and this fuzzy logic model, and you can also use this as a base knowledge to solve more complicated problems in the future, probably the JCY's problem. So I hope I have explained enough. I'm sure you have a lot of questions, so maybe if you can go through the code go through this video, and if you have questions, you can ask me. Either I will explain to you in WhatsApp or phone call, or I can just make another video for better explanation.